friends, hello. Great task today. We are about to dive into one of the greatest scientific theories, a theory that has marked the 20th century, namely the General Relativity of Albert Einstein, no more, no less. In an interview in 1919, the great scientists of the time, Sir Arthur Eddington, have been asked, is it true that only 3 people in the world understand Albert Einstein's theory of relativity? He replied, or better, if you want, he asked, and who is the third? And now we are about to join this distinguished company. We'll do it. What we are going to need is to understand calculus and basic geometry. We start with Einstein's principle of equivalence. In fact, Einstein has introduced 3 key points into science, and those are the equivalence of matter and energy, which is his famous equation E equals mc squared, then the relativity of time, and third, the equivalence of gravity and inertia. So let us start with this third one. What it basically says is that if you are in a box with no windows, then you can't tell the difference between being in outer space and accelerating with an acceleration g, or being in the same box or the elevator on the surface of the Earth, stationary but subject to the gravitational force which carries an acceleration g. There is practically no experiment that we can do that will distinguish between those 2 situations. Strictly speaking, that is actually not quite true. If we are in outer space traveling with an acceleration g, then all parts of the box or the elevator, including us, are accelerating at the acceleration g. On the other hand, if we are on Earth, then the value of g varies according to the height above the Earth. The value of g at the lower point will be slightly greater than the value of g at the higher point, and so there is a slight difference in the value of g in this situation. This difference is called the tidal force. So if we are in the box and we measure that, then we could tell the difference and decide whether we are accelerating with acceleration g or we are subject to gravity. But if we neglect this, the tidal force, we arrive to Einstein's principle of equivalence of inertial and gravitational mass. Another key point that we need to understand is that light bends in a gravitational field. Regarding this, Einstein's reasoning was as follows. Let us suppose that the individual who is in the box accelerating through space with an acceleration g shines a light from one side of the box to the other. By the time the light gets halfway across the box has accelerating a bit further, since a fraction of time have passed, albeit small. The light will have reached the position in the middle of the box or the elevator, a bit lower than the starting one. By the time the light gets to the right-hand side of the box will have accelerated still further, and the light, which is in fact traveling in a straight line, will reach a point which is even lower in the box. The overall impression is going to be that the light has bended towards the lower right-hand side of the box. We obtain a curve. So Einstein's reasoning in this Gedanken experiment is, if this is what happens, the light bends in an elevator which is accelerating with an acceleration g, and due to the principle of equivalence of inertia and gravity, we can't tell the difference whether we are accelerating through space with g or we are standing stationary on Earth, being subject to the gravitational force g. Then we should expect the same thing to happen in the second scenario, and the light to bend in a gravitational field as well. He could have been wrong, but in fact this was shown to be true during a solar eclipse, which happened on May 29th, 1919, his first victory. what happens during a solar eclipse is that the moon essentially blocks the sun for the observer on Earth. The astronomers on Earth could see a star just slightly to the right of the sun on its virtual position, while they knew that the star actually was located behind the sun and its true position should be therefore not visible. So the explanation could have only been that Einstein was right and that the light of that star was being bent in the gravitational field of the sun. But Einstein had another problem, namely Newton's law of gravitation, which have served so good to that point, states that the gravitational force is equal to the gravitational constant multiplied by the mass of the body multiplied by the mass of another body divided by the distance between them, r squared. And that's fine. But in this situation, we have light bending due to the gravitational field, and we are dealing with photons. They are carriers of the electromagnetic force. They move with the speed of light in vacuum, and they are massless. We do have two bodies here. The sun do have mass, but the photons don't. So Einstein suggested completely different approach. He said, what is happening here is that all forms of motion are represented by movement in a curved spacetime. We could visualize the spacetime as a trampoline. We step on it and it bends. We obtain a curved spacetime. We put a small marble nearby. It also curves the spacetime, but to a tremendously smaller scale. And what happens is that the marble is going to fall towards us. Now, what Newton said is that the movement towards us was caused by gravitational attraction, but Einstein thought differently. Einstein, on the other hand, said that the marble is moving along the shortest path in curved spacetime. So when the Earth goes around the Sun in an approximately circular orbit, Newton says that there is a gravitational force between the Sun and the Earth which provides the centripetal force, and this force keeps the Earth in orbit. But Einstein says, no, that's not it at all. What happens is the Sun, being massive, curves the space-time, and the Earth is going around that curve in a straight line. Two questions arise. First, what is space-time? Second, why did Einstein think that it would be curved? So to answer the first question, space-time is really just space and time, all thought of as one set of coordinates. We represent the space with three orthogonal axes. To this, we add a time dimension to obtain a four-dimensional space-time. Often we represent all three space coordinates with just one, x, and then we represent time on the vertical axis. In that manner, if we draw a constant velocity in space-time, we get a straight line. This straight line represents distance divided by constant time, and that is constant velocity. If we accelerate in space-time, we get a curve. The reason, of course, being that acceleration means that the longer the time, the further we go. So to answer the second question, why Einstein thought the space-time is curved will be if acceleration is being represented by a curve and gravity causes acceleration, that means that gravity will require a graph which is curved in the space-time coordinates. Or simply, if gravity is acceleration, for instance, g equals 9.8 meters per second squared, which is acceleration, and acceleration is a curve in space-time coordinates, then gravity must be presented in space-time coordinates as curved. The gravitational field must be presented as curved space-time. So these are the essentials of what we are going to need in our attempt to derive Einstein's field equations, I hope successfully. Without further ado, let's jump to the equation. This is the Einstein's field equation. One might think that is only one equation, but we look closer, we see that there are some indices mu and nu which arise at several places in the equation. This mu and nu represent the dimensions of space-time. Consequently, they might have the values 0, 1, 2, and 3, 0 for the time axis and 1, 2, and 3 for the space coordinates, namely for x, y, and z coordinates. Mu and nu can have 4 values, 0, 1, 2, and 3, which combined gives us 16 field equations. But if we develop the equations, we shall see that 6 of those are identical. They are duplicates. That leaves us with 10 Einstein's field equations. So what is what in these 10 equations? First, G. G is the good old-fashioned gravitational constant, and C must be the speed of light, which leaves us with the following. At the beginning of the equation we have R mu nu. This is called Ricci curvature tensor, which we will derive. Then we have G mu nu. G mu nu is the metric tensor. We will derive this term as well. Then we have R with no indices, which is called the curvature scalar, and we'll show what that it is as well. We also have capital lambda, and that is Einstein's famous cosmological constant. It is the energy density of space or vacuum energy, closely related to dark energy. Einstein denoted once the cosmological constant to be the greatest blunder of his life, but is it really so? We will look at this one as well. Finally, we have T mu nu, which is the stressed energy momentum tensor. We will try to explain what it is as well. The whole point about the equation is that it balances two things. Everything on the left-hand side refers to curvature of space-time, and everything on the right-hand side is to do with mass and energy. So John Wheeler rightly said that in Einstein's field equations, mass tells space-time how to curve, and curved space-time tells mass how to move. In what follows, we shall present first the metric tensors G mu nu. Then we will move to the Christoffel symbol, which is presented with capital gamma. We don't see Christoffel symbol explicitly in the equation, but it is involved in the Ricci curvature tensor. Further on, we'll look at curvature itself, which will enable us to derive the Ricci curvature tensor R mu nu and the curvature scalar R. What we will follow will be the stress energy momentum tensor and then the cosmological constant. Finally, we'll put it all together. Now we begin the mathematics, the metric tensor. Since tensors are algebraic objects defined to describe multilinear relationships between sets of algebraic objects related to a vector space, we might begin with this vector space. Namely, in applications, it is common to study situations in which a different tensor can occur at each point to an object. The phenomenon that we are observing, and for which we choose to use tensors, for instance, the stress of pressure within an object, may vary from one location to another. This variation of the observed phenomenon from one location to another leads to the concept of tensor field. But let us start with the simplest field of all fields, namely a grass field. Let us further on suppose that this field is very bumpy, and let us denote the value of the field on each point as the height above sea level. So we label this height as phi. This is a value we can measure at every point in this bumpy field, and it constantly changes from a point to a point. How do I know where I am in this bumpy field? I could impose a set of coordinates. We have now an x coordinate and an y coordinate. That way our position is uniquely defined, and we have a value of phi for each position we might be on. We can pose the question, how my position changes if I move a little bit. I might find myself on a ridge. If I move along the ridge, that might be along one of the coordinates, say it is y-axis, the value of phi, that is the height, changes a little bit. The ridge is flat in that direction, and the height above c is constant. If I move down along the x-axis, the height changes substantially. So direction of movement is crucial. How can I tell by how much the height will vary as I move along? In order to describe this situation mathematically, we introduce a gradient. Let us say that for every 10 meters that I walk along, I will drop 1 meter. Mathematically, we say d phi, that is change in height as we walk along, is the gradient, which we express as d phi by dx, which is actually the gradient. For instance, here d phi is 1, dx is 10, multiplied by the distance we actually walk, which is dx. For instance, the change in height d phi is the gradient, which is 1/10, 1 in 10, the rate of change, or simply the slope. And let's say I walk 5 meters, so dx is 5 meters. We obtain for the change of height 1/10 multiplied by 5, and that is a half meter change in height. We have calculated that if you walk 5 meters along a 1 in 10 gradient, your height changes by half a meter. Why is this important? Because we have come to the general form of what a change of value of field is, which we'll need for our curved spacetime. So the change of value of field is the gradient multiplied by the distance traveled for small distances. We said the direction of movement is also important. Consequently, the change of height as we travel in the x direction is equal to the gradient in the x direction multiplied by the distance we walk in the x direction, and also the change in height in the y direction is equal to the gradient in the y direction multiplied by the distance we walk in the y direction. If we are walking along a ridge, one gradient will be very steep, x here, and the other one will be level because of the flatness of the field in that direction, y in our case. But we might also walk in a direction which is neither x nor y, as is depicted here. Walking in this new direction, neither x nor y, could be decomposed in two components. That is a combination of walking in x direction and in y direction. We can present these directions here as vectors. That way we are now a step closer to what we intend to arrive to, and that are the tensors. So what we have here is summarizing two vectors, which could be done by arranging the vectors tip to tail. The other is not important in this case. Here the tip of the dx vector is placed at the tail of dy vector. The resultant vector is ds, which is the tail of the first and the tip of the last. Next we'll apply Pythagoras to work out what ds is. We have dx squared plus dy squared, which gives us the magnitude of ds. But we could also use the vector notation by putting a line above the appropriate increment and working with them as with vectors. We now have the vector ds equals dx plus dy. So now the change of height as we go along the path S is equals to the change in height as we go along the path X plus the change in height as we go along the path Y. d phi S equals d phi X plus d phi Y. We have seen previously what these two terms mean. For instance, change of height as we go along X in the gradient multiplied by the distance traveled for small distances. So we substitute these values into the formula we have obtained. More precisely, we shall replace the increments in the gradient terms with delta or a curly d, which is Greek letter, to denote partial derivatives. Why partial derivatives? Because the partial derivative indicates that there are also other derivatives in respect to other variables. Here, for instance, we have derivative in respect to x, but also another one in respect to y. Another change that we are going to make is to replace x, y, and z with x1, x2, and x3. This way, whenever we have to increase the dimensionality of the system, we simply add the appropriate index to x. In case of Einstein's field equations, we are going to work with 4 spacetime coordinates. 0 in x naught will pertain to time, and 3, x1, x2, and x3 to space. If we have another one, then it will be x4. Also, we are going to use y for other purposes just in a while. So now we have d phi, which is the overall change in height in our field phi, to be equal to the gradient delta phi by delta x1 multiplied by the distance plus the gradient in the y direction, now x2 direction, times the distance in x2 direction, plus further terms provided we have such. So now we simplify this by using a sum term to add them together, and we have for our d phi to be equal to the sum over n of the gradient delta phi by delta xn multiplied by dxn. For n equals 1, we obtain the first term, delta phi by delta x1. For n equals 2, the second term, and so on. N is the summation term. We have derived our first important equation denoting the change of the field phi as a sum of all partial increments, the gradients, in all possible directions. We denote this equation as equation 1. Now we arrive yet to another important point, which pertains both to the special as well as general relativity. It is the fact that any rules that we come up with and want these rules to be universally true must be independent of the frame of reference that we are using to make one particular observation. This is depicted on this slide here. In special relativity, it is shown that different observers measure different distances and different times depending on their relative velocity. It is called length contraction and time dilation. So in our field, let us suppose that we are standing at the point P, and let's set a coordinate system x1, x2. So our map reference will be x1 and x2 respectively. Those two values define our position. But somebody else could come along and create another set of coordinates, which we will call y1 and y2. Our position haven't changed, it's P in the field denoted by vector phi. But as far as the y frame of reference is concerned, the coordinates are quite different, y1 and y2. These are different from x1 and x2 in the x frame of reference, even though the position is the same. Also notice that if I want to express y1 in terms of x coordinates, I have to express it both in terms of x1 coordinate and x2 coordinate. And also if I want to express y2 in terms of x coordinates, I need two more values for x1 and x2 pertaining to y2. Next, the question is, if I know all the gradients described by delta phi by delta x in the x frame of reference, how can we find all the gradients in the y frame of reference? And more to the point, how can we relate the two? We will need this for sure if we want to walk through Einstein's curved space-time describing the gravity. For this purpose, we engage the so-called chain rule. Let us pick y1 as a coordinate to which we will apply the chain rule. We may as well pick y2 and then generalize. So we have delta phi by delta x1 times delta x1 by delta y1 plus delta phi by delta x2 times delta x2 by delta y1. We stick here to y1 coordinate, but sum over x1 and x2, sum over 2x coordinates, because we have mentioned that y2 coordinate is expressed through x coordinates. We could generalize and put sum over m for those two terms. We'll have the above expression for two values x1 and x2, and this could be extended from our 2x1 and x2 coordinates to m in general. Also, we have performed the chain rule for y1 coordinate, but we could have picked also y2. So we generalize once again and have delta phi by delta yn, and n can go from 1 to whatever is the dimensionality of y reference frame. It's 2 in our case. We denote this as equation 2, and this equation will help us convert the movement in our field from one frame of reference to another without changing anything but the point of view of the observer. In the following slide, we have vectors presented in two different frames. Next, we shall introduce the concept of tensors. In fact, a great part of general relativity is based on these algebraic objects. So we should know what tensors are. In order to get to the definition of a tensor, we could first begin with a scalar. A scalar is an algebraic object that has magnitude but no direction. For instance, temperature could be a good example of a scalar. It just has a value of, say, 37 degrees centigrade. A scalar could be viewed as tensor of rank 0. Next comes the vector. A vector has both a magnitude and a direction. The vector can be described as a tensor of rank 1. It is often described as the angle to one of the axes. How does a vector transform? We could use the equation 1 we have derived earlier. We can slightly adjust it. So instead of working with d phi and dx, we could replace them with vectors. We can say that the vector v in the y frame of reference and with the coordinate n which we choose is equal to the sum over m, where m is now the summation term of the gradient, which is dyn by dxm. M is the summation term times the vector v, since we are replacing dx with a vector v in the x frame of reference and n. We call this equation 3. The tensors that we will be interested in are tensors of rank 2. Tensor of rank 2 is combination of vectors where there is a fixed relationship between the two. So let us present a system which consists of a block on the floor, and let us apply a force to it in order to move the block in a certain distance x in this direction. We now want to present a tensor to get an idea what it is. The work done will be the force times the distance. But here we have to take the component of the force that is moving in the direction we want to go. If that angle is alpha, then the component of the force acting in the direction of movement is F cosine alpha. The work done will be this multiplied by distance traveled. So we have here two vectors, F and X. X also has a magnitude and a direction. Thus, we have two vectors combined in a certain relation, which is the requirement for a tensor. Let us now suppose that the force F is directed vertically towards the block, so the angle alpha is 90 degrees. The cosine of alpha will be 0, and consequently the work done will be 0, because the block won't move. Now, what's important for us is that no matter what frame of reference we apply to this system, that block will not move. The value of the work done will be 0 in all frames of reference, and that's a tensor by definition. A tensor is a relationship between two vectors, and if the tensor has a value of 0 in one frame of reference, it must have a value of 0 in all frames of reference. More to the point, if that block doesn't move and it doesn't produce work, it doesn't move. The frame of reference is not an informational feature of the system, it's just contextual. The frame of reference gives just a description of the system, not the system itself. That's the relativity in the theory of relativity. The observation is relative, the system observed is absolute, so to speak. So we have defined a tensor. So tensors of rank 2 represent fixed relationship between two vectors, and this relationship is preserved in all frames of reference. That's why they play such an important role in Einstein's field equations. There is a tensor defined for each point in the gravitational field of space-time coordinates. So let us consider a combination of vectors, doesn't matter what it is for. We are going to take vector A, and we are going to take the mth coordinate of that vector. Remember, there are dimensions in space. We are actually using only two dimensions to make the analysis simple, and could be either one or two. We'll take also another vector B, and we'll take the nth coordinate, which also could be either 1 or 2, and we say that the combination of these two, T and N, becomes a tensor of rank 2. This tensor consists of two vectors A and B of two dimensions each. M can be 1 or 2 and N can be 1 or 2. Thus, there can be four versions of tensor Tmn with all the combinations for M and N. If we have three dimensions of space, M and N, and each have value 1, 2, 3, then Tmn would have 9 different values. In our case, in general relativity, we have 3 values for space coordinates and 1 value for time, so we have 4 times 4, 16 different versions of the tensor Tmn. Now we are going to use equation 3 that we derived earlier. In this equation, we are going to replace the value v with a and represent this in the y frame of reference, just as it is done for v earlier. At the same time, replacing n from equation 3 with m in our current equation as a dimension of a, and we obtain the first part of our new equation. Here also we need another term for m of equation 3, since it's already used. So let us introduce r as a summation term, and let's mention that it is sometimes called a dummy variable. It doesn't have other purpose than to serve as a summation term for our sum. In equation 3, we have also a second term vxm, and we replace v once again with a. This time it's in the x frame of reference, the same as in equation 3, and we enter r as a summation term or a dummy variable as an indicator for our summation, and as we see, it's the same as m in equation 3, which we are replacing. In the same manner, we add the term byn in order to obtain later on our tensor. Then from equation 3, once again, we replace the term v, this time with b. We work once again in the y frame of reference, and finally introduce the value of s for a new summation term in the place of m from equation 3. Once again, because the value of m is already used. So our second summation term, or a dummy variable, is s. We also add b to multiply this term, the same as v above in 3. It's in x frame of reference and has s as a summation term instead of m in 3, which is used for other purpose. We change the sequence of the terms, grouping together in the front the partial differentials and then multiplying them with the correspondent a and b. Now we have the equation presented here on the slide. But a and b in n is a tensor of rank 2 tmn. Also, the second term of this same form, arbs, is a tensor trs of rank 2 in the same manner as above. This second tensor is in the frame x of reference. Thus, we have the tensor of rank 2 tmn in the y frame of reference on the left side of the equation, and by doing the above transformations based on the equation 3, we have obtained another tensor of rank 2 on the right side of the equation, and this new tensor is in the x frame of reference. So it becomes visible now that what we have obtained is a transformation of a tensor of rank 2 in y frame into another tensor of the same type in the x frame of reference, which has a set of partial differentials in front. In the future, we could use this new equation as a tool for transforming a tensor from one frame of reference, y in this case, into another tensor of the same type, but now into another frame of reference, x. This transformation is called contravariant in general relativity. So great. Since general relativity has as one of main features the curved spacetime as a mise-en-scène or a background, we could be happy to have such a useful tool to use in the future in our derivations of the Einstein Field Equations. Let us first denote this obviously useful equation as an equation 4. If this is a contravariant, what would be the covariant? It should exist an equivalent form of transformation. We could guess that this would be the operation which performs the opposite transformation, the other way around, namely converting a tensor of rank 2 from the x frame of reference into the correspondent one in the y frame of reference. In this case, when converting a tensor from x to y, we write the indices downstairs instead of upstairs. What is important here in the covariant transformation, when we go from x into y frame of reference for tensors, is that instead dy by dx, we must have now dx by dy. We call this covariant transformation equation 5. Once again, contravariant have the indices upstairs, covariant have the indices downstairs. Contravariant have dy by dx terms, covariant had dx by dy. Why? Conditionally speaking, if we observe the covariant form, we are in the x frame of reference. If we change dy from the left side to the right, dx denotes moving in the independent x direction by small increments dx, and dy changes accordingly. In short, In the covariant transformation, the indices go downstairs instead of upstairs as in contravariant. We put y in brackets. This is where we go from x prime. Then we have the summation term over r and s. Then the terms from equation 4 go upside down. dym by dxr becomes dxr by dys. Then the same for the second term. And finally, the tensor has its indices from the summation terms, the dummies, written downstairs. For us, the covariant form of transformation will be of interest. Next, we will need a bit of Pythagoras. Pythagoras applied to a right angle triangle, and if this is the x1 using our frame of reference in the x frame of reference, and this is x2, this is s, the hypotenuse, then of course we can easily say that according to Pythagoras, ds squared is equal to dx1 squared plus dx2 squared. If there were further dimensions, we would have this plus the other terms dx3 squared, or in short form, that is simply the summation over m of dxm times dxm. M goes from 1 to whatever dimension we have. We'll have the x1 squared plus dx2 squared and so on. We may also write ds squared is sum over m and n, and then have dxm times dxn, and then make variations of m and n. If we do this, we see immediately that this is correct when m equals n, but it is not correct otherwise. So what should we do in order to be able to use this form? We shall see later on why. We may introduce a form called Kronecker delta here, or delta mn, which says delta mn is 1 if m and n are equal, and it is 0 if m is different from n. So in this way we multiply dxm with itself when m is equal to n and Kronecker delta is 1. And when m and n are not equal, then we multiply by 0 and eliminate those unwanted terms. Now we have got this elegant form of Pythagoras. In this way, with Kronecker delta symbol, all the cross forms go out. Now we go back to the equation 1. We'll write it in a slightly different form. Instead of d phi, we write the term dxm. We have delta phi also on the right side of the equation, and it also becomes delta xm. So we replace x from equation 1 with y and n, which is an index from equation 1 and summation term, with r. X becomes y, and consequently dxn becomes dyr. We'll omit the summation term as Einstein did. The summation term is implied here with r as a dummy. So I suppose Einstein considered this form more elegant, or simply he used this to avoid constant and repetitive writing of the summation term. We will do the same. We do the similar replacement to the second term in Pythagoras. dxn becomes sum of delta xn by delta ys dys. Again, it's based on equation 1 and the summation term is omitted. So the Pythagoras equation becomes, after these two replacements, ds squared equals delta mn sum over rs delta xm by delta yr dyr multiplied by delta xn delta ys dys. As on the slide. Next, we change the sequence of the terms. We rearrange them. First goes Kronecker delta, then delta xm by delta yr multiplied by delta xn by delta ys, and finally dyr times dys. We have put the gradient terms together and then the rest. This is form of Pythagoras. But now this term here in the block denoted in lavender is called GMN or metric tensor. And finally, this is something we have seen in Einstein's field equations. We have come to something. What is the metric tensor? We could see in the equation, if we compare it to the Pythagoras, that it is a kind of extended Kronecker delta. We could write that ds squared is the metric tensor GMN times dyr dys. It is Pythagoras for curved space. Let's remember that is also a summation term in the beginning neglected by Einstein as implicit. It is obvious that for flat space the metric tensor is reduced to Kronecker delta term. We could see here that for curved space-time coordinates the triangle could have many different forms and that the sum of the angles is not 180 degrees. We see that GMN in flat space is identical to Kronecker delta and equals 1 when R equals S and 0 when R does not equal S. Well, in the flat space, Pythagoras was simply the summation term with the Kronecker delta, which made sure we didn't get any cross terms. Here in curved space-time, we have exactly the same thing, but instead of having just a simple Kronecker delta, we have got now a more complicated metric tensor. The formula well known to us for flat space ds squared equals dx1 squared plus dx2 squared is not true, obviously, in curved Einstein's gravitational field. And how we deal with it? With the fact that Pythagoras does not apply to a curved spacetime, we make the correction by introducing the metric tensor GMN. Now let us have a quick look at Einstein's field equations to see what we have done so far. We have derived the metric tensor in the equations. There are 16 of them obtained by combining the indices in the tensors 4 by 4. 3 coordinates for the space and 1 for time, combined in tensors of rank 2. These 16 reduced to 10 due to the fact that 6 of them are duplicates or identical to each other. We notice we have mu and nu here instead of m and n. That's a consensus to use these terms mu and nu when presenting curved spacetime. Both mu and nu are used for space and time. The value 0 is used for time and 1, 2, 3 for space. So that's the great value of metric tensors. It pertains to the metrics of spacetime. Even roughly, they may be thought of as a generalization of the gravitational potential of Newtonian gravitation. We could expand the application of metric tensors from spacetime also to distance, volume, angle in the curvatures, or even separation of past and future. This if we take into account that the indices also present time with the possibility to present an event in space-time with past and future. By changing mu and nu and other parameters, different space-time metrics in Minkowski diagrams could be obtained, as we see on the slide. But back to Einstein. Now let us derive the Christoffel symbol, which plays one of the major roles in the Einstein Field Equations. Now let's suppose that we have a tensor named W. Let us suppose it has n and m coordinates in the x frame of reference, and we'll say that it is equal to another tensor V, also with n and m coordinates in the x frame of reference. Let us start by stressing once again one important fact about tensors. Namely, the important thing about tensors is that they represent a fixed relationship between two vectors, and they are independent of the coordinate system. In particular, if one tensor is 0 in one coordinate system, it will be 0 in all coordinate systems. We could take once again the example of the field at the beginning of the video. If the height of the field is 2 meters, it will always be 2 meters, no matter what frame of reference we are talking about. But there is a problem here, namely the problem is that the derivatives of tensors do not necessarily transform between frames of reference in the same manner, and we are surely going to need derivatives of tensors. So we have to find out what happens here. So let's take a tensor in the x frame of reference, which we'll call Tmn in the x frame of reference. And let's say that it equals the derivative of a vector v with respect to x in the x frame of reference. Now the question is, does the same tensor Tmn in the y frame of reference equal the derivative of the vector v with respect to y in the y frame of reference? Is that true? The answer is no. To find out how to deal with this problem, let's go back to equation 5. Later on we'll drop the summation term just as Einstein did. Here we rewrite the first two terms as they are in equation 5 and replace TRS of x with the appropriate value given as delta VR of x by delta xs in the x frame of reference with r and s as dummy variables. We need to sum over the summation terms. We have changed m and n to r and s. Now if we look at this marked combination of terms here on the slide, what we have got is essentially the inverse of the chain rule. So we could contract the expression by eliminating delta xs, and we obtain delta VR of x by delta yn. Now we have the contracted form given here, and we ask, does this equal delta Vm of y delta yn? That's the question we have started with. So does it equal? Is the question. Let's just write that term, delta Vm of y by delta yn. We could use equation 5. It refers to equation 5, which is actually a tensor term, but the tensor of rank 2 can be reduced to a vector just by dropping one of the two vectors. Let's do it. We can see that delta Vmy by delta yn could be written as delta by delta y of Vm of y. And now we take Vm of y from equation 5, but drop one of the vectors. We have now a delta y from equation 5. We take the first term, delta xr by delta ym, drop the second derivative term, since we are now reducing the tensor to one single vector, and replace TRS of x with VR in the x frame of reference VR of x. We have v instead of t, since it's the vector we have started with. We have omitted the dummy variable s, so instead of rs as indices, we have just r. And r is a dummy variable of the summation term from the sum, which is implicit here. Einstein was omitting the summation terms, and so we are. Now we are supposed to find the derivative of a product, and that's done according to the rule DAB equals ADB plus BDA. So now delta Vm of y by delta yn will be the first term, delta xr by delta ym times the derivative of the second term of the product, delta xr by delta ym times delta Vr of x by delta yn, plus the second term, which we write at the end, times the derivative of the first term. And the derivative with respect to y of the first term of the product is delta by delta yn times delta xr by delta ym. Now observe that this term here, delta xr by delta ym, delta Vr of x by delta yn, is equal to the term in Tmny in the y frame of reference. So we were asking, does that term there, Tmny, equals this term delta Vm of y by delta yn? That was the question. Why? Because we have started by wanting to examine whether a tensor, which is a derivative of a vector v in one frame of reference, is equal to the derivative of v in respect of y in y frame of reference, while this derivative in y is the same with that same tensor in y frame of reference. In other words, we wanted to know whether, while tensors remain the same in different frames of reference, the derivatives of tensors stay the same as well by transforming from one frame to another. And now we find out, yes, we have exactly the same term in y, but we also have in y another term, delta by delta y and delta xr by delta ym times Vr of x. And what precedes the vector v in this extra term we name the Christoffel symbol. So in this way we have derived another important symbol and ingredient of Einstein's field equations, and this is the Christoffel symbol. So this combination of differentials is called Christoffel. It's called gamma and denoted with capital gamma. We represent also the indices that appear in this combination of derivatives, which represent gamma. We put r, which is upstairs in the derivatives, also upstairs in gamma, and n and m, which are downstairs in the derivatives, we put also downstairs in gamma. So we have gamma, mn, r. So while Tmn of x equals delta Vm of x by delta yn in x frame of reference, Tmn of y is not delta Vm of y by delta yn. There is an extra term, gamma. Now, in order to get around this extra term, which is the Christoffel symbol, we say that Tmn does equal a new concept, which we will call the covariant derivative. That's what that symbol means. Hence, in tensor calculus, we don't have an ordinary derivative, we have a covariant derivative, and we denote it as nabla Vm and call it covariant derivative. What is the covariant derivative? It's the ordinary derivative of v delta Vm by delta yn, which we thought might be the derivative in y frame equivalent fully to the one in x, but it was not. Instead, it has an extra term, which is the Christoffel symbol, a correction term multiplied by Vr of x. We denote this equation 7. We can ask, what is this Christoffel symbol? It's the compensation for the fact that the ordinary derivative of a tensor in one frame of reference does not transform in a straightforward manner. we need the covariant derivative in order to have transformation of a derivative of a vector, which is a part of a tensor. A lot of the Einstein Field Equations require derivatives of tensors. We have done that with vectors. Now we have to expand that to tensors. So let's take the covariant derivative. We are going to use P as an index because we will need M and N also in a moment. We are going to use the equation we have just derived, equation number 7, but in a way that we are going to double the indices and thus expand the equation from one vector, which was part of a tensor, to two vectors. In that way, we'll expand the equation to a tensor of rank 2. We have first the ordinary derivative delta Tmn by delta yt. Then we use our Christoffel in the same way as used in equation 7. One Christoffel for the m element and another Christoffel for the n element. So then we have delta Tmn by delta yt, p instead of n in 7. Then the first Christoffel with p upstairs, then pm for the m element and pn for the other. Let us title this equation 8, and we have the transformation of a covariant derivative of a tensor from one frame of reference to another, from x to y. Now what about the covariant derivative of the metric tensor that we derived earlier? Let's just remind ourselves what the metric tensor was. We started off with Pythagoras, where we had x1 and x2 and also ds as a hypotenuse. We say that ds squared equals dx1 squared plus dx2 squared plus all squared for higher dimensions. We have seen also that we could rewrite that as sum of dxm times dxn times Kronecker delta. We have seen that Kronecker delta was 1 when m equals n, and it was 0 when m does not equal n. This Kronecker delta is gmn for flat space. But the metric tensor gmn is not 0 when m does not equal n, when the space is curved. Gmn, the metric tensor, is not the same as Kronecker for curved space. This is why it was invented to play a role of Kronecker delta for curved space. For curved spacetime, Kronecker delta expands to metric tensor. So that's what a metric tensor Gmn was, a correction for curved spacetime. The reason we have the metric tensor Gmn is to correct Pythagoras for curved space. Now, what is the covariant derivative of Gmn with respect to r in the x frame of reference in flat space? In flat space, the metric tensor is either 0 or 1. It reduces to the Kronecker delta in flat space. So it's a constant. The derivative of a constant is 0. The derivative shows the change, and there is no change when we have a constant. Thus, the covariant derivative of the metric tensor is 0 for flat space. But the metric tensor is a tensor, and for tensors it is valid that if the tensor is 0 in one frame of reference, it will be 0 in all frame of reference. Consequently, if the covariant derivative of the metric tensor is 0 is one frame of reference, it will be 0 in all frames of reference. We have equation 8 for covariant derivative. This equation showed the transformation of a covariant derivative from one frame of reference to another and introduced Christoffel symbol in order to do this and extend the ordinary derivative into covariant derivative. Because, sadly, if a tensor remains the same in all frames, we have seen it is not correct for the derivatives. That's why we introduced Christoffel. Back to 8, we replace all t's with g's, all tensors t with metric tensors. No reason not to do that, since metric tensors are tensors. and we equal the equation with 0. We got this equation here. Now we have got an equation which has the metric tensor in it and the derivative of the metric tensor and the Christoffel symbol. So we ought to be able to rearrange that equation so that we can express the Christoffel symbol in terms of the metric tensor. Instead of having the metric tensor and its derivative expressed in terms of Christoffel, we want to express explicitly the Christoffel in terms of metric tensor and its derivatives. Maybe Einstein asked Biljana to help him for this one. So if we do that, what we obtain is the following equation. We title it equation 10. What can you say about the Christoffel symbol? Firstly, it's not itself a tensor, it's a correction term. Christoffel will be equal to 0 in flat space, but it won't be equal 0 in curvilinear spacetime. We could also notice that it can be expressed fully in terms of the metric tensor and the first derivatives of a metric tensor. It does not feature in Einstein's field equations. We could not see it in these equations. We could see the cosmological constant, for which Einstein said it is the greatest blunder of his life, but not the Christoffel. It is not visible. Yes, we don't see the Christoffel in Einstein's field equations explicitly because it is hidden in the Ricci curvature tensor, and we do see the Ricci curvature tensor in the equations together with the cosmological constant. Christoffel symbol is buried in the Ricci curvature tensor, and that's what we are going on to next. Now our next topic is curvature. We are going to talk about curved spacetime, so we need to understand what curvature means. Let us take a path in a flat space. We can suppose this monitor is flat. We take a vector. The vector has a magnitude and a direction. What we do when dealing with flat space, we walk around a path in a manner of what we could call a parallel transport. While walking around a closed path, our vector keeps the same length and we keep it oriented in the same way, so it travels parallel to itself. All the positions of the vector traveling along the path in a flat space are parallel until we get back where we started. When we arrive, our vector will be the same length and same orientation. But it's not the case if we have a curved space or space-time, for instance, if we have a ball. We start at one point, we move in the same manner as around a closed path in a flat space. We walk in a manner of parallel transporting. The vector keeps its length and its orientations. It moves in the same way parallel to itself. But when we arrive at the starting point, the vector does not match itself from the starting position. It has now quite different angle and orientation. So there is a difference. We have to deal with it somehow in general relativity. We see that when we parallel transport a vector in a not flat space or curved spacetime, when we arrive at the starting point, the length of the vector is the same, but the direction of the vector has changed. This changed direction can be used as a measure for the curvature. There is an angle between the starting position of the vector and its final position after we have done the parallel transporting. This angle change is the way we can define the curvature. But we'll need two definitions first. The first one refers to what's called a commutator. It's written with square brackets. The definition of commutator is commutator AB, and that's A times B minus B times A.
Of course, if we are simply talking about pure numbers, then that will equal 0. 5 times 6 minus 6 times 5 equals 0. The point about commutators is they don't always equal 0. Let's look at one in particular. We have the commutator of d by dx and some function of x. We are going to show that that actually equals df of x by dx. It doesn't equal 0. A quick proof, a commutator is ab minus ba, so this is going to be delta by delta x f of x minus f of x delta by delta x, as is visible on the slide. We have got to apply d by dx to something, so let's just call it v. But we have a differentiation of a product in the first term. It is by definition dab is equal to b dA plus a db. We have v, the second term of the product, times differential of the first, delta f of x by delta x, plus the first, which is f of x, times the differential of the second, delta v delta x. The second and the third term are equal, and the one minus the other one is 0. We eliminate them. Then v is something we inserted, so we can now take that out. The result is that the commutator is equal to df of x by dx, which is what we wanted to show. It's not 0. So let's now take two coordinates which do not necessarily have to be right angles. This is the x mu coordinate, this is the x mu coordinate. Also, we are going to have a distance in one direction, which is dx mu, and distance dx mu. We construct a parallelogram from that where the length of the two horizontal sides are going to be dx mu, and the length of the other two will be dx mu. Now we are going to do a parallel transport around this path. We are going to go from A to B to C to D and back to A again. We are going to call the return point A prime. We are not sure that vector will be exactly the same when it gets to A prime. The vector of A prime might not be the same as the vector at A if we have gone around a curved surface, not a flat one. We now take two paths. The first is VC minus VD. That's essentially that we are talking about. There is the difference between the vector at point C and the vector at point D, and compare that with the vector at point B and the vector at point A. VC minus VD minus VB minus VA. Now, if we are going around a flat surface, then VC minus VD will equal VB minus VA, and that whole term will equal 0. But what this is actually representing is the differences in the dx mu direction, because that's the directions that we are moving here. Similarly, if we take the VC minus VB, which is this path here, minus VD minus VA prime, we get the difference in the dx mu direction, because that's that path there. They are parallel in flat space, there would be no difference, but in curved space there might be, and we are now looking at the difference in the dx mu direction. Now let's have a look at the difference of the differences. If we take this term here, VC minus VB minus VD minus VA prime, and we subtract from it this term here, VC minus VB minus VD minus VA prime, then what do we get? Let's have a look at the VB term. We have got a minus VB and a minus minus VB, that becomes plus, so we get a minus and plus equals 0. We get no resultant VB term. Then we have a plus VC minus VC, the VC term goes. And regarding VD, we have got a minus VD, minus minus VD, so it's plus, and the VD term goes as well. What about VA? We have got a minus minus, so that becomes a plus. So we have got VA, and then for VA prime we have got a minus minus minus, so 3 minuses, and that becomes minus VA prime. And that's the difference of differences. That's going to be the change in the vector as it is parallel transported around that parallelogram. We denote this difference as dv. In flat space, dv will be 0. The vector will come back to where it started off with same magnitude and the same direction. But if it is in curved space, there will be a difference not in the length but in the angle of the vector. Now let's take this first term here, Vc minus Vd. What actually is that? That is the change as the vector goes from C to D along the distance dx mu. So Vc minus Vd is simply the change in the vector along the distance dx mu delta V by delta x mu. That's the gradient. This is multiplied by the distance we travel, which is dx mu, multiplied by the vector itself. So what we are saying is that the change in the vector between C and D is the gradient. We did this right at the beginning with our field. But we have just learned that we need to be very careful about ordinary derivatives. When we are talking about curves, we have to use the covariant derivative. So actually, to be more accurate, we better call this the covariant derivative. Thus, instead of using this gradient, we are going to use the covariant derivative, nabla mu times dx mu times the value of the vector. That's a much healthier way of doing it, because we have learned that we have to be careful about ordinary derivatives when we are transforming between different reference frames. Now, what is this term? Vc minus Vd minus Vb minus Va. That is the difference in the differences on a line which is separated by the distance dx mu. So essentially what we are doing is we are looking at the difference of vectors with a separation of dx mu, which means we have to apply a new gradient to it. So Vc minus Vd minus Vb minus Va, which is, as we said, the difference in the vectors in those two lines separated by different distance dx mu. Well, we said that Vc minus Vd is the covariant derivative times the distance times the value of the vector, but the difference, the minus, is essentially another differential, and it's the differential in the new direction. So we have now got to add a covariant derivative in the new direction times the distance away dx mu. So that is effectively what the difference equals: Vc minus Vd minus Vb minus Va. What about this one here? Vc minus Vd minus Vd minus Va prime. This one will be just the opposite. In other words, Vc minus Vb minus Vd minus Va prime will be Vc minus Vb will be the covariant derivative, but this time in the new direction. So now we need covariant direction in the new direction times dx mu times the value of the vector v. But this subtraction means that we are looking at the difference between this line and this line, red line is vertical, separated by dx mu. Essentially, we are applying another covariant differential, but this time in the mu direction. So we have now got that this covariant differential times the difference away dx mu, as we see in the slide. This term Vc minus Vd minus Vb minus Va equals on the right side to the covariant derivative in the new direction, dx mu times covariant derivative mu dx mu times vector v. From that term, we subtract Vc minus Vb minus Vd minus Va prime, which equals on the right side to the covariant derivative mu dx mu, covariant derivative mu dx mu times v. And we get Va minus Va prime equals dv, which is the difference between the vector at the starting point and the vector at the end point. So if we subtract this term from this term, we are going to get dv. dv is the difference in the vectors. So dv is going to be equal to, dv is covariant derivative mu dx mu times v minus covariant derivative in the mu direction times covariant derivative in the new direction times dx mu times dx mu times v. Then we can pull out dx mu and v, because again doesn't matter here in which order we put these terms. So what is left is covariant mu minus covariant mu, and that we recognize as simply the definition of commutator. Simply is the commutator, covariant derivative mu, comma covariant derivative mu. These nablas are covariant derivatives. We remember that from equation 7, the covariant derivative is equal to the ordinary derivative, it's just a shorthand, plus a gamma term. Remember that was the corrective term, our Christoffel symbol. Once again, wherever we have this covariant form, we'll remember from equation 7 that the covariant form is the ordinary derivative plus this corrective term which involves the Christoffel symbol. On that basis, the commutator which we identified before is going to be equal nabla mu equals to delta nu plus gamma nu, the Christoffel, times delta mu plus gamma mu minus delta mu plus gamma nu times delta nu plus gamma nu. We have the first term of the commutator times the second minus the second term times the first one, which is what a commutator is by definition, while we remember that the covariant derivative is the ordinary derivative plus the Christoffel term. So we now get that is equivalent to covariant nu, which is delta nu plus the Christoffel associated with nu, times the term which is actually covariant mu, which equals delta mu plus the Christoffel symbol associated with mu, minus the same terms in switched order. Now let's just multiply that all out. So we have got delta mu plus gamma nu delta mu plus delta nu gamma mu plus gamma nu gamma mu minus the other term, and we multiply that as well, and we got for the second term delta mu times delta nu plus we have got delta mu gamma nu plus gamma mu delta nu plus gamma mu gamma nu. Next is the subtraction. Let's do the subtraction. Delta mu minus delta mu is equal to 0, because for ordinary derivatives the order doesn't matter. Next, gamma nu delta mu minus delta mu gamma nu will form a commutator. In fact, that is equal to the minus commutator of delta mu gamma nu, which is all expressed here on the slide. Next, we have got another commutator here, delta nu gamma mu minus gamma mu delta nu, which is the commutator of delta nu gamma mu. And finally, we have got gamma nu gamma mu minus gamma mu gamma nu, and that again is going to be the commutator of gamma nu gamma mu. To summarize, what we have obtained here was the commutator of the two covariant vectors, covariant mu here, or two covariant terms, becomes this term here, 0 minus delta mu comma gamma mu plus another commutator delta nu gamma mu plus another commutator gamma nu gamma mu. But remember, when we first made the digression to introduce the commutators, we have said that when we have a function like the one we have here, this equals the derivative of the gamma term with respect to x mu, as it is presented at the slide. And the second commutator involving gamma becomes the derivative of the gamma term with respect to x mu. Once again, this comes from the proof we have given about the commutators, that when we have commutators delta delta x, comma f of x, this gives delta f of x by delta x. We have proved that briefly earlier. Finally, this entire term is called the Riemann tensor. Great. We can notice that it is made up of Christoffel symbols and derivatives of Christoffel symbols. For our purposes, it can also be regarded as the Ricci tensor, which we meet in Einstein's field equations. The Ricci tensor was the first term in the Einstein's field equations. Let's have a look once again. So what we have just shown is the change in the vector. Remember, that's what we have been looking for. We wanted to find the change in the angle of vector rather than the length, which doesn't change, while parallel transporting the vector along the curved spacetime. And that's the essence of Einstein's view on moving through a gravitational field. That change we have seen is equal to delta x nu times v times the commutator of covariant mu, and for this last term we have said that it was the Riemann tensor. Once again, for our purposes, it's Ricci tensor. Before we proceed, let's make an assessment and just take stock of where we have got to. We have shown that the Ricci tensor is made up of Christoffel symbols and the derivatives of Christoffel symbols. But what are Christoffel symbols made of? In equation 9 we have seen that they are made of metric tensors and the derivative of metric tensors. And what are metric tensors? They can be thought of as the device we need to correct for Pythagoras on a curved surface or curved spacetime. So great. So what is next? We see in the Einstein's equations that we also have something called scalar curvature. What is that? We can derive this scalar from the Ricci tensor directly. This element is a scalar, not a tensor, not a vector. We could remind ourselves that if we take a dot product of two vectors, we get a scalar.
In the similar manner, we can take the Ricci tensor and from it we can create a curvature scalar. The point about that is if the curvature scalar is not zero, then the surface is not flat. Let's just review where we have got to. We have covered the metric tensor, G mu nu. We have covered the Ricci tensor, R mu nu, which includes a lot of Christoffel symbols. We have covered the curvature scalar R. We have covered most of the terms of Einstein's field equation. There are just two more terms to go: the stress energy momentum tensor, P mu nu, and the cosmological constant capital lambda. We deserve a break. We are now ready to do the stress energy momentum tensor, P mu nu. First, we ask the question, what is the shortest distance between 2 points? The answer is a straight line. What is the shortest distance between 2 points, say, on the surface of a sphere? Not 2 points on a circle, but 2 points on the surface of a sphere. The answer is that the shortest distance is a construct which is called a geodesic. For instance, on the Earth, the equator is a geodesic. Any line of longitude is a geodesic. The shortest distance between 2 points where we have to go around the curve and we can't go in a straight line is called a geodesic. Next, we can define what's called a tangent vector, dx mu by d tau, as a rate of change of the distance that we travel with respect to time. We'll be using tau because tau is what's called proper time. And what is proper time? In relativity, proper time is the time which all observers can agree on, no matter what frame of reference they are in. So if we use tau as a symbol, we know that there can be no arguments about what we mean. We want to find the rate of change of distance with time, and that's called a tangent vector. The derivative of that tangent vector must equal 0 in order to find the minimum distance. Generally, when we want to find the minimum of a curve in respect to some parameter, we take the derivative and we set it to equal 0. That way we find for which value of the independent variable we'll have the extreme of the function. And then for that value we find the exact value of the minimum. You know that. It can also give us the maximum, but in this case, in this context, we'll have the minimum. So if we take the derivative of the tangent vector and set it to 0, we will get the shortest distance. In this case, we'll find the path of the geodesic. To be precise, since we are in the realm of general relativity and curved spacetime, we wouldn't be working with ordinary derivatives, but with covariant derivatives. We have derived equation 7 for covariant, and we could see that that will be essentially the ordinary derivative plus a gamma term. We have seen that. We'll remember that gamma was the correction for curved space. So we follow the equation 7, which is applied on the vector v, but we apply it on our tangent vector dx mu by d tau. We get d by d tau applied on dx mu by d tau instead of d by dy n as in 7, since we are looking for a shortest distance traveled in time. We use the proper time tau. We get delta by delta tau, delta x mu by delta tau, plus we add the correction term for covariant derivative, which is gamma. We have essentially a double differential here with respect to time. It is delta 2x mu squared, and what This is like 2, we could see is the acceleration. So is the rate of change of distance with time, delta 2x mu by delta tau squared. It equals 2. Since this acceleration plus gamma equals 0, the acceleration will be minus gamma. On the other hand, let's remember that general relativity and Newton's law of gravitation should be the same when we are just talking about ordinary masses and low speeds. We are not talking about black holes here. Newton's law of gravitation nicely describes what appears to be gravity. Thus, in the simple case, general relativity and Newton's law must conform to the same thing. Newton's law says that force is mass times acceleration. Here, our acceleration is a force term divided by mass. On the other hand, we have got an acceleration is equal to a minus gamma term. What we can say is that the gamma term is the equivalent of force in Newton's law. There will be a mass term in it as well, but mass is constant, so let's forget about it. We could assume it's 1. The gamma term, the Christoffel symbol, has a kind of broad equivalence to force. G is equivalent to F. Next, we'll need the equation 9 that we derived for Christoffel symbol. It consists of metric tensor plus derivatives of the metric tensor. But here we are dealing with a situation where we have low gravity, low speed. We are not in black holes. We are observing just ordinary space and slow movement. General relativity must reduce to Newtonian gravity. When that happens, G becomes 1, and the derivative terms are very, very small, with one exception, and the exception refers to time. Time, remember, has mu and mu equal to 0, so the delta G not by delta x, the time component, is the only term in the derivatives that has any significance. All the rest, all the other terms could be neglected when we are talking about slow speed, small masses, and no black holes. This term GAD becomes 1. All the other terms in the derivatives are approaching 0. A gamma term reduces to 1/2. GAD becomes 1, so we can ignore that. Multiply it by all of the rest, which reduces to simply delta G 0 by delta x, the time term, which is the only one not to be neglected. Gamma becomes 1/2 delta G not by delta x, for which we said was equivalent to a force term. So the force is kind of equivalent to this term here. On the other hand, in Newtonian mechanics, force is minus the derivative of the potential. For example, if the potential energy near the Earth is equal to minus mgx, where x is the height above the Earth, then the force will be minus d phi by dx, which equals minus mg, after we perform the differentiation in respect to x. The minus term simply indicates that the force is acting in one direction, while x is measured in the other direction. So all we are showing here is that in Newtonian mechanics, force is minus the derivative of the potential phi. Now we just show that the Christoffel symbol capital gamma is the equivalent of a force term, and in ordinary space, where we're not anywhere near black holes, that is equal to the derivative of the time component of the metric tensor with respect to x, as it is shown on the slide. We have also just shown that force is minus the derivative of the potential with respect to x, and so we can see that if gamma is a force term, these two terms are broadly equivalent, delta G 0 by delta x and delta phi by delta x. We multiply by 2 and
integrate. Thus we get that G naught naught is equal to 2 phi plus an integration constant. We can forget all about the constant because as soon as we differentiate again, that constant will go. What we're saying is that because the Christoffel symbol gamma equals 1/2 delta G00 by delta X, and Christoffel symbol has a kind of force equivalence. G is equivalent to F. Also in Newtonian mechanics, force is equal to minus delta phi by delta X. That is minus the differential of the potential energy. Then we can therefore equate these two terms, 1/2 delta G naught naught by delta X and delta phi by delta X. And if we equate those two terms, essentially the metric tensor or the time value is equal to 2 times the potential energy plus a constant. Now we said that force is minus delta phi by delta X, but we really need to do that in 3 dimensions. So that normally reduces to what is called divergence of phi. The divergence term is simply delta by delta x plus delta by delta y plus delta by delta z term, which should be minus there. We also know from Newton's law of gravitation that the force F is equal to minus g, the gravitational constant, times the mass of one object times the mass of the other object, divided by the square of the distance between them. So let's consider an object of mass m, and let's consider a distance r from mass m, and we ask ourselves the question, what is the force acting on a unit mass placed at distance r from m? The unit mass means the mass is 1, lowercase m. The force F will be minus gm over r squared because m is 1 now. And next, what is therefore the force capability across the whole of that surface of the sphere? That's going to be the integral of f dA, where dA represents the area of the surface of the sphere. That's going to be the integral of the force, which is minus gm over r squared times dA. If we integrate out, that is simply going to be equal to minus gm over r squared times the entire area of the surface of that sphere A of radius r, which is 4 pi r squared. The r squareds cancel, so we find that that reduces to minus gm times 4 pi. Now there is a theorem called the divergence theorem. What does it say? Let us write it up. It says that the integral of f dA over an area is equal to the integral over the volume of the divergence of the force. Integral f dA equals integral of the divergence f dA. What that means is that the outward flux through the area of the sphere is equal to the volume integral of the divergence of the force. That's the divergence theorem that can be derived. The divergence theorem could be written also the other way around, and we see that the left side is an integral volume over the volume V. All 3 dimensions of the volume are included, and that's the volume over the divergence of the force. The divergence represents the change of F in all 3 directions. The right-hand side is the surface integral over the boundaries of the volume V. In physical terms, the divergence of a vector field is the extent to which the vector field flux
behaves like a source at a given point. It is a local measure of its outgoingness, the extent to which there is more of the field vectors exiting an infinitesimal region of space than entering it. The divergence represents the volume density of the outward flux of a vector field from an infinitesimal volume around a given point. The volume density of the outward flux is spread over the surface. But back to our problem in hand. The density is mass divided by volume, rho equals m over v, and therefore we can say that the mass of an object will be the integral of the density with respect to volume, m equals integral rho dv. Now we are going to take f, which we calculated to be integral f d8 equals minus gm for pi, and set it equal to this term, integral of the divergence of f dv, which was the divergence theorem. Now we have that integral of f dot dA is minus 4 pi g times m. For m, we are going to use the integral of rho dv, density times volume. That's the integral of f dot dA, and that's going to be the integral of the volume of divergence of f dv. Minus 4 pg integral rho dv equals integral of the divergence f dv. We solve the integrals. Roughly speaking, practically we can cancel out the dv's, although it's not really proper to do it. Essentially, what we are left with is that divergence of f is equal to minus 4 pi g rho. We have shown that the force is minus the derivative of the potential in Newtonian mechanics, F equal minus divergence of pi. We have also just shown that the derivative of the force is equal to minus 4 pi g rho. Consequently, if the force is minus the derivative of pi, the derivative of force is the derivative of minus the derivative of pi, and that equals minus 4 pi g rho. In other words, minus the derivative squared of phi of the potential equals minus 4 pi g rho. The minuses on both sides cancel. Earlier we showed that the time component of the metric tensor g naught naught equals twice the potential plus a constant, which means that the potential is a half of the metric tensor. Phi equals 1/2 g 0, 0. We may drop the constant. There's no problem in doing so, because as soon as we do a derivative squared of phi, which is this term here, derivative square of phi equals 4 pi g rho, replacing phi by half g 0, 0, the constants will all go. So now we have got that the derivative squared of phi is 4 pi g rho. Next, the derivative squared of half the time component, the metric tensor, equals 4 pi g rho. And if we multiply both sides of the equation by 2, we get that the derivative squared of the metric tensor equals 8 pi g rho. Now the problem with that is it's not a tensor equation, and for general relativity we need a tensor equation. So what we are looking for is something that looks similar to it, where at the left hand side we have a tensor, and also on the right hand side we should have a tensor. G mu mu equals 8 pi g t mu mu. Basically, we want something that has the form of G mu mu, which is actually called Einstein's tensor. It is equal to 8 pi g, but instead of having the mass density term rho, we want a tensor for energy, something that contains all the mass, energy, stress, pressure terms that we can have. And this is actually how we derive the stress energy momentum tensor. This g mu nu is called Einstein's tensor. G mu nu equals 8 pi g t mu nu. So we have essentially got to find something for t mu nu and something for g mu nu. Let's look at the t mu nu side of it first. With this, we shall come much closer to Einstein's field equations, which are r mu nu minus 1/2 g mu nu r plus g mu nu lambda equals 8 pi g over c squared times t mu nu. In order to find suitable candidates for t mu nu, we have to use a result from special relativity. That's an element called momentum 4 vector. This 4 vector coming from special relativity has, as usual in special relativity, 1 dimension for time and 3 dimensions for space. This vector is p equals m, and the component are x0 over tau, the time component, the x component x1 over tau, the y component x2 over tau, and the z component x3 over tau. In this momentum for vector, we have mass multiplied by x0 over tau, x1 over tau, x2 over tau, and x3 over tau. We operate here with 4 dimensions in space-time divided by tau, which is the so-called proper time. In relativity, proper time is the time which all observers can agree on, no matter what frame of reference they are in. It is shown in special relativity that if we reduce the first term x0 over tau, we get mc squared, which is energy, the famous Einstein's equation. In the other terms, all effectively become the momentum in the different coordinates. We have mv in the x direction, mv in the y direction, and mv in the z direction. So this 4 momentum reduces out to basic rest mass energy mc squared plus momenta in the 3 coordinates of space. That's fine, but that is essentially still a vector and we need a tensor. So the momentum 4 vector from special relativity reduces out to basic rest mass energy plus momenta in the 3 coordinates of space. As I said, we need not p but t mu nu, a tensor, and that means we need a 4x4 matrix. So without further ado, let's draw one. This is the matrix. And there it is. We can see that t has all the values of mu and nu from 0 to 3. And what do all these values mean? Well, the top one, t naught naught, that is going to be the time component of the stress energy momentum tensor. And that has the following kind of equivalence. It's t naught naught is equivalent to mx0 over tau, which corresponds to mc squared. The time component is the density of relativistic mass. This is the energy density divided by the speed of light squared. Its components have a direct physical interpretation. In the case of a perfect fluid, this component is T00 equals rho, the density. The 3 components along the top here, in the first row, we are going to call the energy flow parts of the tensor. The 3 components in the first column, we are going to call the momentum density of the tensor.
And the 9 components which are left are essentially the momentum, flux, stress, pressure parts of the tensor. So this is the momentum, flux, stress, pressure. Those components are embodying every part of energy that we can think of, whether it be pure energy, rest mass energy, momentum density, energy flux, pressure, shear stress, and so on. All of it somehow finds a place in this stress energy momentum tensor. It is in a way a measure of energy per unit volume. These are animations of different aspects of the changes of the components of a stress tensor, presented on the slide. All the possible directions of the change are shown. The stress energy tensor, also known as energy momentum tensor, represents the quantity of energy and momentum, so in a way of energy and matter at a particular point in space-time. The stress energy tensor field represents its distribution over all points of space-time. The animation further on shows a few kinds of tensors in general. We can see that a rank 3 tensor requires 3 pieces of information to find the component, Kij. The rank 4 tensors require 4 pieces of information to find the component, Kijl, in the animation. But as physicists say, a tensor is what transforms like a tensor. That's a tensor. Back to Einstein. We said this tensor is in a way a measure of energy per unit volume. E over volume equals Wk over volume. That is presented here. Now energy has the same units as work, so we can think of this as work per unit volume. Work is force times distance. Distance is length, volume is a length cubed, so that's equivalent to force divided by a length squared, which is force over area. And this represents units of pressure. So that's how energy per unit volume can also embrace pressure or stress. The stress energy momentum tensor contains 16 different terms, some of which it turns out are duplicates. It comes in the form of a matrix. It embodies all forms of energy, and it's the stress energy momentum tensor that we use on the right hand side of the Einstein Field Equations. Now on the right hand side we have got the 8 pi g rho that we derived, but we are going to replace the density term rho that we came up with this new stress energy momentum tensor, 8pg t mu nu. We've seen that in a way density is equivalent with stress. On the left hand side now we have something. What could it be? What we have on the right hand side is the mass term. On the left hand side we need something that is the space-time curvature term. So Einstein thought that the obvious candidate for it would be the Ricci curvature tensor, R mu. It would represent 16 different values at each point in space-time, as does T mu. But there is a problem here. The problem is that we have a law that governs the universe, and that's the energy conservation. Energy can be neither created nor destroyed. So if we take the derivative of the energy tensor, it should be 0, since there is no change in energy. It's a constant. Delta T mu nu is 0. The problem is if we take the derivative of the Ricci tensor, it does not equal 0. Delta R mu nu does not equal 0. So that equation can't be true because the derivative of one side would be 0, while the derivative of the other side would not be 0. We should not forget that we are talking about general relativity and field equations, so we cannot use ordinary derivatives. We must always use the covariant derivative. Thus, if we have stated that the covariant derivative of the energy side is 0, delta T mu nu equals 0, we need something on the left-hand side whose derivative will equal 0. What Einstein actually found was that the covariant derivative of the Ricci tensor was not 0, but it actually was 1/2 times the covariant derivative of the metric tensor times the curvature scalar. So the covariant derivative of Ricci tensor R mu nu equals 1/2 of the covariant derivative of the metric tensor times R times the curvature scalar, which we spoke about earlier. So this is the equation he discovered. Here we can bring everything to one side, and essentially we get that the covariant derivative of the Ricci tensor minus 1/2 times the metric tensor times the curvature scalar equals 0. And we have got this equation here. Now we have a covariant derivative of this term equals 0, and we also have the covariant derivative of T mu nu equals 0. Therefore, those terms for which we are finding covariant derivative must be equivalent. So now we have got the left-hand side of the equation R mu nu minus 1/2 G mu nu times R equals the right-hand side of the equation, where it's not just T mu nu, but of course is 8 pi G T mu nu, and we are almost there. R mu nu minus 1/2 G mu nu times R equals 8 pi G times T mu nu. It turns out for dimensional purposes, we need to have a C to the fourth term here. Essentially, that's just a constant for dimensional purposes. But Einstein realized he had forgotten something. We should remember that earlier we showed that the covariant derivative of the metric tensor equals 0, covariant G mu nu equals 0, and because it equals 0 in one frame, therefore it must do it in all frames. Therefore, we could have included the metric tensor in this equation here, covariant derivative of R mu nu minus 1/2 of G mu nu times R equals 0, not just as a multiplier of R, but in its own right. It equals 0 in all frames of reference. Even more, we could have included it with any constant in front of it. And that is what Einstein did. So Einstein therefore decided that we needed to include this term, which is 0 in its own right, covariant derivative of G mu nu equals 0 in this equation again. So we have now covariant derivative of R mu nu minus 1/2 G mu nu times R, which is this part of the equation here. And now we need to include the fact that we could have had a metric tensor term in here. So we'll add it, and we will have a constant which we shall call capital lambda multiplied by the metric tensor. And all this equals on the right side to 8 pi gt mu nu divided by c to the fourth. This c to the fourth was added for dimensional purposes, as I have mentioned. This part, we'll remember, was the Einstein tensor G mu nu. What is this capital lambda term? Well, it's called the cosmological constant. It's the famous constant for which Einstein said that was the greatest wonder of my life. but maybe it's not a blunder. Einstein first thought of this constant while he was trying to identify how we could describe space in mathematical terms. He was told at the time that space was fixed and unchanging. In his famous Philosophiae Naturalis Principia Mathematica, Newton defines absolute time and absolute space. The cosmological constant lambda could be thought of as the energy density of space, or the famous vacuum energy. Also regarding gravity, the gravity would tend to make all galaxies pull together. That's not happening, so there must be something which is balancing gravity and pushing the galaxies apart. It must be that the gravitational attraction is being balanced by something that's pushing them apart. Einstein found that he could reintroduce that something which balances the gravitational attraction and pushes the galaxies apart into his own field equations as a constant that is multiplied by the metric tensor. This term is a very, very small term, and we often find it to be left out of the Einstein's field equation. It only becomes relevant when we are working in the realm of major cosmological scales. So that's it, my friends. We have derived Einstein's field equations. Let's remind ourselves that mu and nu are, of course, the time and space dimensions, 0 for time and 1, 2, and 3 for space. Therefore, there are 16 equations considered there. 6 of them are identical to another 6, so the number reduces to just 10. And that's it. Let us finish with something Einstein said. I never ask about future, it comes soon enough. Thank you.